In this video, we're going to discuss the concept of an equivalence relation. At least we're going to formulate its definition and look at some examples. So, given a set X, whose elements are as displayed here, let us color this in with green color. So we've got a green set X. Let us label the elements with numbers. So let's say the elements are 1, 2, 3, 4, 5, 6, 7, and 8. All elements distinct. All of these points are distinct elements as they have been given distinct names. Well, I mean, in general, if you give distinct names to two things, it doesn't mean they're distinct. For example, if I call X an object X and another object Y, it might happen that X and Y are the same object. But when we give a concrete name, like with numbers, so that the idea then is that this object actually represents that number, then of course, because the numbers are different, then the object must be different as well. The same thing cannot represent two different things. Okay, so we've got 8 different elements in this set, and an equivalence relation on a set is a relationship that kind of tells us that certain elements are similar or the same or equivalent. In this specific case, we could form an equivalence relation in many different ways, but let's choose one of them, and we can form in the following way. We could say that two numbers in this set are equivalent when either they are both even or they are both odd. And this relationship of two numbers being both even or odd turns out to be reflexive, symmetric, and transitive. So you can see every number is of the same kind as itself, right? So 1 and 1 are both odd, obviously, and then 1 and 3 are both odd, and 1 and 5 are both odd as well. But then well, first of all, the relation is clearly symmetric, because if 1 and 3 are both odd, then also 3 and 1 are both odd, right? So the direction doesn't matter when we say both are of the same kind. And so it is also transitive, because if 1 and 3 are both odd and 1 and 5 are both odd, then 3 and 5 are also both odd, because they're both of the same kind as 1. So that's exactly transitivity, right? So 3 is related to 1 and 1 is related to 5. That should give that 3 is related to 5. And indeed, 3 and 5 are both odd, so they're related. And then 5 and 7 are both odd numbers, so these are related as well. And all the numbers among 1, 3, 5, and 7 are also interrelated because of transitivity, right? So we've got all these lines here as well, and also a line joining 1 and 5. Now, it comes to the point where we have a bit of a messy picture with many lines, but let's keep it like this for now. And let's now look at number 2 and things that are related to number 2. And let's mark them with a different color so we don't mix it up with the other ones. Let's use yellow color for that. So 2 and 8 are both even, so they're related, and 2 and 4 are related, and 4 and 6 are related, and 6 and 8 are related, and then 2 and 6 are also related, and 4 and 8 are related as well. And what we see here is that essentially what's happening here is that two groupings are emerging. The grouping of the odd numbers and the grouping of the even numbers. And this is actually a feature of equivalence relations in general. They group a set into disjoint grouping. So I could now make a nicer picture by changing the location of the displayed elements. So let this be 1 here, and 3, and 5, and 7. And on this side I'm going to have 2, 4, 6, and 8. And now I can see that instead of drawing the lines, I could just have these shaded with a different color, and then the information that is given by this new picture is the same information that the old picture gives. It just tells us that any two things you've got in that same grouping, you can just connect them, all of them, with each other through arrows, through lines, and that's how you get a description of the relation behind the procedure of grouping these things, right? The relation of two numbers being either both odd or both even. Now, in general, in an equivalence relation, it doesn't have to be so that the groupings have the same size. So in this example, it turned out to be that in both cases we have 4 elements in each grouping, but this doesn't have to be the case. And to illustrate that, let's change the example a little bit. Let's add another number here, number 9, which will now fall in the grouping of 3, 1, 7, and 5, because it's an odd number. And I actually should add all these lines and make the picture even more messy. There we go. It's not easy to do that, but it's much easier to do it on this side. And so now we've got an equivalence relation where the groupings that have been created by the relation are not of the same size. So basically, an equivalence relation being a relation that's reflexive, symmetric, and transitive, these 3 properties are what makes it possible for the relation to be represented as a collection of groupings. This is going to be dealt later on with the concept of partition. Actually, what we've got here, this display is a display for a partition, and the link between the notion of a partition and equivalence relation will be thoroughly explored using formal mathematical proofs. But at the moment, it's just sufficient for us to get the intuition, and we still want to think at this stage of an equivalence relation not as such a picture, but as such a picture with the lines, because they represent the related pairs. But in the back of our minds, we have this idea that every such distribution of lines actually gives rise to grouping of the set. So just to look at another example, let's take a set Y. And now let us consider elements of Y to be balls of different color. So let's say we've got a red ball here and there and there, and then we've got a yellow ball here and there and there, and then we've got a blue ball. And we can now consider a relation that on the set that says that 2 elements are of the same color. And once again, just like with that of being same, of both numbers being either odd or even, here the relationship of being same color will be reflexive, symmetric, and transitive. Obviously, every ball is of the same color as itself, so that's that's reflexivity. And if one ball is of the same color as another one, like this one is of the same color as that one, then also in reverse direction it holds that the other one is of the same color as the first one. So that's symmetry, right? And if now one ball is the same color as the other one, and the other one is the same color as the third one, then obviously the first one will be the same color as the third one, so that's transitivity. So you see, once again, we've got these lines which interconnect all the balls of the same color, and eventually we're going to get a grouping of the set Y into 3 groups which correspond to the 3 colors that its elements obtain, right? So here we've got the grouping of balls that are red, and here we've got the grouping of balls that are yellow, and here we've got the grouping of balls that are blue. Maybe actually I should maybe use a different color for that. And so if I had to display this relation using lines like before, then I would have to connect every two element in the same grouping, like that. And once again, we see that the picture with the groupings is much neater than the one with the lines. Now let's look at a final example of a relation. In this case, it will not be an equivalence relation. So let us consider again numbers as elements: 1, 2, 3, 4, 5, 6, and 7. And in this case, let the relation be of inequality. So when one element is greater or equal to the other one. So, for example, 7 is greater or equal to 6. But now it's not sufficient to have a line without an endpoint, because this relation is not transitive, right? 7 is greater or equal to 6, but 6 isn't greater or equal to 7. So now we have a line with an arrow at the end. So the typical mapping line we use for functions. And 6 is greater or equal to 5, and 5 is greater or equal to 4, and 4 is greater or equal to 1. Also, obviously, 4 is greater or equal to 3, and 3 is greater or equal to 2, and so on. And I'm actually going to erase this one, because I can get it by joining the others. And this relation is obviously transitive, right? So 7 is greater or equal to 5, and 5 is greater or equal to 3. Therefore, 7 will be greater or equal to 3. So that's the transitivity property, the one that allows us to join the arrows. It's also reflexive. Every number is greater or equal to itself, right? But it fails to be symmetric. 7 is greater or equal to 6, but 6 is not greater or equal to 7. And because of this failure, it's not an equivalence relation, because an equivalence relation needs to have all the three properties. And also we see that it is now impossible to make a grouping description of this relation, because as long as we do the grouping description, it automatically, first of all, it automatically erases the direction of the arrows. And then if I do a grouping, well, it will have to be one whole group, because there is an arrow from between any two numbers. But in that one whole group, without the direction of the arrows, then it will appear as if also the backward relationships hold, which is not true, because, for instance, 3 is not greater or equal to 4. So for a relation to be describable by such grouping display, it has to be actually reflexive, symmetric, and transitive. This is something that's going to come up later in the material. And in other words, it has to be an equivalence relation, and failure for symmetry already doesn't allow us to have the grouping description anymore. Same is true for reflexivity and transitivity. If we make either reflexivity and transitivity fail, we will again get failure of the description of the relation just by grouping of its elements. So we've got here two examples, well, three. Two are examples and one is a counterexample for an equivalence relation.